Hello everyone. This is lecture series 1 for class 10 students. We'll study about the concept of moment of force and would try to relate to what are those effects that are produced when you apply a force on a rigid body. So in class 9th we know that when you apply a force on a rigid body, so suppose this is a rigid body. And what kind of body is known as rigid body? Rigid bodies are those wherein when you apply a force, it only causes the motion. There is no deformation happening. The size and the shape does not change, but motion occurs. So as a result of application of force on rigid body, suppose this is the force that you apply, and we consider this body is placed on a table. And suppose this table is frictionless. Then this force is going to cause a motion. It's going to get displaced. So there is linear and translational motion of this body. So translational in the sense it's going to traverse linearly further upon application of force. And suppose multiple forces are acting. Suppose you have one force here, and let me draw it again here. And you have the same frictionless table, but here you are applying a force, suppose in this way, F1. And we know this force is pushing. So it could be either pushing or it could be pull. It could be pulled up. So that is this push and pull is what is known as force, right? So if F is the force and the direction of the force is this, and you are applying another force in the opposite direction, suppose, and F1, the magnitude of F1 is more than F2, this is placed on the same frictionless table, then what's going to be the effect? The effect is, although this force is opposing the motion, which is caused due to this, but since this is more than F2, since F1 is more than F2, we'll get the motion in this direction, and the net force because of which this motion is getting caused, this force or this resultant force is what is the real cause of motion. So according to second law of Newton, it says that this net force is causing an acceleration of this body. So this body was at rest, and you apply a force F1 in this direction. The another force simultaneously is from the other direction. The difference of these two is the net. Why? Because F1 is more than F2. This force is opposing this. So what is the resultant? The resultant is F1 plus negative of F2, which means F1 minus F2, it comes out to be F net, which is the applied force. So this is the applied force or the resultant force. And according to Newton's law, this is the force responsible. This is the force responsible to cause a motion. And to cause a motion means that there is change in speed. This is a condition we considered this body initially at rest. With the application of this net force, this body which was at rest has now a speed. So there is a change of speed. Per unit time, the change is known as acceleration. And we know this equation of motion, equation of Newton's law, which says that this force, this net force is equal to mass times acceleration. So acceleration is in the same direction as that of force applied. Alright, so having understood this, that this force can cause linear or translational motion in both situations. When you have this force, there is opposite force, however, there is a linear motion. Now this force that we are talking about, which is causing a motion, can also produce another effect, and that effect is rotational motion. So the force that we took an example in case of translational motion. This causes translational motion, and it also causes rotational motion. So it can cause both kind of motion, rotational motion. So when it is going to cause a translational motion, the force is going to cause a translational motion when you have no fixed and the body is free to move. The body is not fixed anywhere and it is free to move in any direction. It's going to be a translational or a linear motion. However, if you have a situation wherein, suppose we take an example with this. This is a disc and you fix this disc on this axis of rotation, which means that this is a pivot about which you would allow this to move. This is fixed, and you are also ensuring that the distance of this outer part is fixed. So this point is fixed, one end is fixed, and the distance is also fixed. And now you apply a force. So if you draw the diagram, suppose you take a rod like this and you ensure that you fixed one end, and this is the axis of rotation. Suppose this is axis of rotation. And this point that you have fixed, it's known as fixed axis or fixed point, which is also known as pivot, which means that it would allow this to move about it. However, it will not allow to move away from it. It will allow to move about, but it will not allow to move away from it. And this distance from this fixed line, from this fixed position, this distance is suppose r. And you are applying a force in this direction, suppose, in this direction. So we can label this as line of action of force. Line of action of force. What do you think? Where would be the net effect of this force eventually will cause the effect? So what effect it's going to produce? So this force, which is perpendicular to this distance, is going to produce a turning effect. And this turning effect is what we are calling rotational motion. This turning effect that we are calling moment of force, moment. This turning means moment, right? Now, take an analogy. Suppose you tie a rope on an animal's neck, and you ensure that this distance of the rope, the length of the rope remains constant, and the other end of the rope is fixed into one point, or you place one axis of rotation and you fix it, ensuring that this length doesn't collapse, the other end to which the animal is tied up, and then you drive that animal. The only motion that animal can trace or traverse is going to be a rotational motion. Why? You have fixed one end and the other length is also fixed. So the only way or the only option left with the animal to move is around it. And that's what's known as rotational motion. So here's what's happening. This is the axis of rotation. And here you're applying the force. And it's going to produce a rotational motion. So this is what? This is actually radius, right? And this circular path at this point, wherein you are applying a force, if you extend this is what the line of force is. So we know that a tangent with the radius always makes 90 degrees. So with these two conditions, this force is going to produce a rotational motion. And this turning effect is what is known as moment of force, and it's also known as torque. So let us understand more in terms of mathematical expression. So what we have learned until now is that this kind of arrangement is there. If this kind of arrangement is there, then there will be a turning effect, and this turning means moment of force, then moment of force, and this moment of force means torque. This torque is depending upon two quantities. One is the force, the magnitude of the force, and another is the perpendicular distance of this line of action of force from fixed axis. So the product of these two quantities is actually moment of force. So we'll write magnitude of force times perpendicular distance of the line of action of force from the fixed axis. So this is the definition of torque, that this is equal to the product of these two quantities. You can take note of it. Now we need to understand this as well. Let's take the example again of this disk. Now you have the axis of rotation here. So what we need to know here is that if you apply a force here in this direction tangentially to the axis, to this plane, this radius, tangentially you apply a force, which is the line of action, it's going to produce the effect, the turning effect, the rotational effect in this direction. The axis of rotation is perpendicular to this plane. This is the plane wherein rotational motion is taking place, right? And the axis of rotation is this black rod that we are looking into it. So this is the axis of rotation, which is perpendicular to the plane of this. So the effect is either it could go in this way, this direction, and this direction. So this one, here you have the axis of rotation, right? So either when you apply a force, either it could be in this direction. So this is anti-clockwise, right? So this is anti-clockwise. It's going anti to the clockwise direction, opposite to the clock direction. So it is anti-clockwise direction. Conventionally, we take this direction as positive. And the opposite is, it could be clockwise direction, right? The opposite to the anti-clockwise in a clockwise sense. So this could be in this direction as well, and we take clockwise direction as negative conventionally. Now another thing that we need to understand here, if this is so, that if it is in this anti-clockwise rotation, then this quantity torque is a vector quantity, right? This is a vector quantity. As it is a vector quantity, it has a magnitude, which is magnitude of force, the product of force as well as perpendicular distance of the line of action of force from the fixed axis. But what is the direction? The direction is the direction of this axis of rotation. So if it is in anti-clockwise sense, it is coming, this direction of rotation is going to be towards the observer, right? So suppose if you have a cap of a bottle and you are turning this anti-clockwise, eventually you would find this to be opening up. When it gets opened up, it comes towards the observer, right? When it is opening up, and it opens only in anti-clockwise sense. So when it is coming towards the observer, we take it positive. If you do the other way around, when you close this and this, you perform clockwise sense of rotation, it closes. So like a screwdriver. So a screwdriver in this plane, it moves in anti-clockwise direction, which means that it opens up the screw, which means that this this screw is coming towards the observer. But if you close it, it's going to tighten up. It's going to go inside it's going to go away from the observer. It's going to go inside the other object on which you want to screw it. All right. So this is another very important aspect related to this, that it's a vector quantity. So it has to have a direction, and the direction is towards the axis of rotation. So if it is anti-clockwise sense, it's positive, we take as convention, it comes outward towards the observer. And if it is clockwise sense, it goes away from the observer. That is where the direction comes into picture. Now let's talk about the SI unit of it. So we know that magnitude of force is newtons. So let's talk about the SI unit of torque. So we know from our equation that moment of force, which is torque, is equal to magnitude of the force, times perpendicular distance of the line of action of the force from the fixed axis. So it's a product of these two quantities. So the SI unit would be, this is Newton, this is meter, right? So the SI unit is 1 Newton meter for torque. Now 1 Newton meter, you can also convert this into corresponding CGS unit. And we know this Newton can be converted into dyne if you multiply by 10 raised to the power 5. So 10 raised to the power 5 dyne times 10 raised to the power 2 centimeter is equal to 10 raised to the power 7 dyne centimeter. So this is another CGS unit that you can express the SI unit of torque. You can also express in terms of gravitational unit, that is 1 kilogram force meter. So we know this 1 kgf, right? 1 kgf is equal to 9.8 Newton meter. So we can have this equation that 1 kgf meter could be written as 9.8 Newton meter. You can also have another way of expressing this in 1 gram force centimeter. So we know this 1 gram force is equal to 10 raised to the power minus 3 kilogram force, and 1 meter or 1 centimeter here is equal to 10 raised to the power minus 2 meters. So if you replace this here, we can get this 1 gram force centimeter is equal to, if you multiply this, it comes out to be 10 raised to the power minus 3 kgf times 10 raised to the power minus 2 meters, which is equal to 10 raised to the power minus 5 kgf meter. 10 raised to the power 5 kgf meter. Now if you want to convert this, we know 1 kgf meter is equal to 9.8 Newton, right? So if you want to replace this, you need to multiply with 9.8. So let us multiply this and figure it out what comes out to be in terms of 1 gram force centimeter. So you're getting here 1 gram force centimeter is equal to 10 raised to the power minus 5 times, now 1 kilogram force is 9.8 Newton and meter remains as it is, right? So this is equal to, therefore this is equal to, we can say 9.8 times 10 raised to the power minus 5 Newton meter. And we know this Newton meter can be converted into dyne and centimeter, right? So we can have this also written in this way, 9.8 times 10 raised to the power minus 5. And if you want to convert this, straight away we can multiply with 10 raised to the power 7 dyne centimeter. So this comes out to be therefore 1 gram force centimeter is equal to 9.8 into 10 raised to the power. So minus 5 and 7 comes out to be 2. 10 raised to the power 2 dyne centimeter, which is equal to 8 by 10 into 100 dyne centimeter. Therefore, we can write this as 1 gram 4 centimeter is equal to 980 dyne centimeter. So these are few conversions that we should know when we are trying to understand the units of torque, different units that are used here. So we'll continue with some examples of moment of force in the next lecture. Watch it further. Thank you.